Hi everybody, my name's Oscar, this is Noah, and Michael's not here, but he'll be in here shortly. And our sponsor is Frederick Air Conditioning, and they can show us with the problem. So they want to make this air conditioner more efficient by using the condensate that already builds up from the condenser. And their current design, this slinger ring on the fan, right? So what this slinger ring does, it kind of slings that water that's already in the water reservoir onto these coils in the front. But it kind of does a U-shape, so it's not very effective and it's not very controlled. So what we did, we came up with a design that actually recirculated that water that's building up right there, and it's actually distributing evenly.
So 1 watt of power for 250,000 units costs $54,000 over the course of a 6-month period in a year. And so this right here already costs 10 watts. So this is $540,000 that this costs you to run a year for 250,000 units. And so one of the problems with this is that it's very fragile. The warranty cost, this is the most fragile piece inside the unit. It just breaks so much. And the other problem is complaints of the noise. Because when the water is, when you grab the water, it like splishes around in there and it makes just a bunch of noise. And so the other thing on is that my pump and my system has already, our pump and system has already been running this entire presentation. And you can't even hear it. So that's one of the key features of ours. And then I'm going to hand it back to Oscar for the engineering design.
After a lot of thought process, a lot of brainstorming, our main focus was how are we going to get that water from the water reservoir on the top to the actual coil, how are we going to get it? So after a lot of trial, a lot of just thinking around, throwing ideas, we came up with the idea that we use a filtration system using a filter and a pump. This filter is actually going to stop any debris or dust that builds up in the water and get it to the actual pump, which the pump is going to get the flow into our 2 trays that we have on top of the coil, which is actually designed from scratch, and it's a 3D tray with 4 different channels on both sides of the trays on the coil. If y'all want to look at it. Awesome couple power capillary mat. This capillary mat acts like a sponge. So it soaks up all the water that's coming from that tray system, and it evenly distributes on top of the coil system. But the main thing is like, how are we actually validating? How do we know that it's actually working?
Okay, so yeah, now we got water picking up from the system, going in this tray, and we can see that the water is dripping down. But how can I measure that? How can I measure how much water is going in between these coils right here? So what I ended up doing is I cut the bottom of this AC unit, as you can see right there, and I fabricated some sheet metal to make a seat. Along with 3D printing these trays, they sit right here, so when I run the water, I can collect and see how much volume the water is going to each section. Now from there, I know I got more water in my system, but how much of a temperature decrease does that make? That's why we went ahead and installed all these thermocouples in order to read the temperature when we introduce water into the system. And I'll let Bernie talk about the results.
Well, the first thing to consider is that we have the highest temperature at this section. Why do we have the highest temperature at this section? Because the refrigerant is coming out of the compressor. Now, this is important because if we have the most water running out of this section, we can have the most heat transfer, which means also higher efficiency. Now, whenever we were designing our new tray, we figured out a way to make the water drip factor in a higher way in this section. As you can see on our graph over there, the first one, we have the most water dropping at section 6, which is right here. Now, we needed some data to validate what's going to this calorimeter real quick, right? So to get this data, we did a temperature test where we run the system without our modifications, and we saw that we had a temperature of 126 Fahrenheit. Whenever we run our system, it was like 115, so it was a 11 degrees Fahrenheit difference. Then that gave us enough validation to get into this calorimeter improvement, which what they do is simulation of the outer of the apartment and the inner side of the apartment. The outer side is going to have 95 degrees Fahrenheit, and the inside is going to have 75 degrees Fahrenheit. Using this data, we could get the EER, which is the energy efficiency ratio, and the power consumption. Now, whenever we tested their old system, they got 715 average watt consumption. Whenever we turn our system on, we got an average of 687, which is almost 30 watts decrease. Now, talking about EER, we got, with the old system, 12.08 average, but with our new system, we got 12.68. which is a 0.6 decrease or a 5% increase. Now I'm gonna
Closing everything up and wrapping it up. Okay. So at the start, they gave us a problem statement. We went and introduced a brand new system. We figured out how to collect data on that system, and we showed you the data. Now, the real highlights. All right, when Noah mentioned at the start, we mentioned that 1 watt, 250,000 units over a year, that's around $50,000 in energy consumption. Think about when we say 30 watts, which is what we did, and the big impact we're going to make. Not only that, EER, you go to any AC unit company, and they're going to tell you that that's the most important thing. If we would have got a 1% increase, they would have loved it. We got a 5%. And not only that, we have a plan to make this thing even better. One other thing to highlight, we had a budget of $5,000 and we solved the problem in $400. Think about if we would have used the extra budget, where we could be. So going from there, our next solution would be to injection mold our 3D trays. And also there's a water reservoir in the evaporator that sits around 35 degrees cooler than this water right here. If we implement that, the sky's the limit.
That's cool. Great job, guys.